In this video, we're going to talk about the importance of accuracy and precision and to discuss the concept of significant digits. So accuracy is how close the measured value is to the true or the accepted value. So for example, if you used a balance to find the mass of a known standard 100-gram mass and you got a reading of 78.55 grams, your measurement would not be very accurate. Now, precision is how close together a group of measurements actually are to each other. It also can refer to the exactness of a measurement. So one important distinction between accuracy and precision is that accuracy can be determined by only one measurement, while precision can be only determined with multiple measurements. That's why in science we often do multiple trials in an experiment to make sure that the pattern is repeating itself. So sometimes we use the dartboard analogy to help explain this concept of accuracy and precision. So if you would imagine a person is throwing darts and they're trying to hit the bullseye. The closer the dart hits the bullseye, the more accurate his or her tosses are. But if the person misses the dartboard with every throw, but all of their shots are landing close together, they can still be very precise. So in this first example, they have low accuracy. They're not hitting the bullseye, but they have high precision because all of their darts are hitting in a similar region. This one here, this is the goal, high accuracy, high precision. So all of the darts are hitting near the bullseye and close to one another. So they're both accurate and precise. This one here, the darts are hitting close to the bullseye, but they're not very precise because they are scattered around the bullseye. So there's high accuracy but low precision. And then this example, this would probably be how I play darts. There's both low accuracy and low precision. Every dart is missing the bullseye and landing at random places around the dartboard. So significant digits. So anytime we measure something, there will be some error involved. So no measured quantity is exact. There could be reader error, or if you're timing something, you might stop the stopwatch a millisecond too late. There's all kinds of error involved in measured quantities. But in order for us to determine the accuracy of a measurement, we use significant digits. And significant digits are numbers considered to be exact. So if we give an example here, I am 161.2 centimeters tall. That is not exact. That is a measured quantity, so it's not exact. But then there are 16 students in our class. That is exact because it's a counted value. So counted values are, there is no error, but measured quantity, there is always error. So there are some rules around significant digits. So all non-zero digits are considered significant. So in this number right here, 125, there are 3 digits that are significant. The next point can get a little confusing. Zeros are only sometimes considered significant. So they are significant. One of the ways that they're significant is if the zero is found between 2 non-zero digits, like this one here. So 101, this 0 is significant because it's acting as a placeholder between the ones, and we would say that this has 3 significant digits. In this example, zeros are sometimes significant. They're significant if they follow a decimal, as long as the decimal or the number is greater than 1. So in this example, we have 1.00. So we are reporting, when we write this number, that we know that these values are 0. So, and then that could be 1.001. If we've rounded off here, we know, we are certain of these 2 digits. So this is 3 significant digits, but they're not considered significant if they're placeholders. So in this example, 4,000, this is just telling us that the 4 is in the thousands place. All of these are just placeholders. So this is only one significant digit. This one too, because all these leading zeros are just showing us where the placeholder is. So this is only one significant digit as well. So in calculations, we need to be careful of our significant digits. So our answer can never be more accurate than the least accurate part of the question. So you should have the same number of significant digits as the quantity in the question with the least number of significant digits. So for instance, if I added 1 plus 1.0, so if we demonstrate that, so 1 plus 1.0, my answer would be 2, not 2.0, because this only had one significant digit. So we'll go through some rules about adding and subtracting and multiplying and dividing. So in adding and subtracting, you keep the same number of decimal places as the lowest number of decimal places, as I demonstrated in that last example. So right here. So 13.5 plus 14.066 is equal to 27.566. But our lowest decimal place was, our number of decimal places was 1, so we have to report that answer actually as 27.6. So we don't reduce our number of significant digits until we've completed all of our calculations. So we don't round off until the very end. In multiplying and dividing, the answer should have as many digits as the number with the fewest digits. So this one, we have 95.2 times 54.35 divided by, this should be up there, 100.33. That equals 51.571056. But if we take a look at the one that had the fewest digits, it was this one. So our answer needs to be reported in 3 significant digits. So 51.6 would be our answer.